Good day, everyone. I'm very excited to be at this event. I am presenting the glacial record of the Marinoan snowball earth of Namibia on behalf of Professor Paul Hoffman, who could not be here. So, what is it about? It's a stratigraphic record of a snowball earth from the foreslope of a warm water carbonate platform. So I'm here to give you a very complex lecture on snowball earth. So just to give you a little bit of background about snowball earth, so what it actually means is a time period in Earth's history when most of the continents were covered in ice. And in geological history, we only have 1.5% of snowball Earth events. So Earth can exist in different states of climate. So we have, So we have a situation where you have, first of all, glacial, interglacial states. This is represented by this particular globe. So clouds have been left out for easy identification or visualization. And then we have got states without large ice sheets. That is represented here on the upper part of the slide. And finally, we've got panglacial or snowball states. This happened during the Cryogenian and is represented by this part. So because of ice albedo feedback, the climate system cannot pass smoothly when you are in this state between the states, only through violent, irreversible transitions. So this is if you are in the snowball state. So if you look at the snowball states, they are self-terminating through accumulation of normally outgassed carbon dioxide, which cannot be removed from the snowball atmosphere in the absence of rain. Any carbon dioxide ice that forms at the poles in winter sublimates away in summer. So you have this situation up here. When carbon dioxide gas reached critical concentrations, the ice cover melted away rapidly, lowering planetary albedo. So this is what I just said here. And the carbon dioxide would only be drawn out through rock weathering. But before this, you would have an intense greenhouse aftermath lasting until enough carbon dioxide was drawn out by rock weathering. So where is this site located? In the northwestern part of Namibia, which is on the African continent. That's where the site is located. And as I said earlier, snowball epochs are long-lived events because of the carbon dioxide threshold that takes long to be reached. So the first Cryogenian snowball lasted 56 million years. Starting at 717 million years. The second snowball lasted 6 to 16 million years, ending at 635 million years ago. So Franz Fontaine Ridge, which is this small picture here, is located on the coastal escarpment of Namibia, northwestern Namibia, and the Neoproterozoic carbonate platform blankets the then subtropical Congo Craton. So this is what you are seeing here. So this is the Congo Craton. The carbonate succession on the southwestern cape of the Congo Craton is called the Otavi Group. The Fransfontein Ridge is special in that it exposes a southward dipping homocline, exposing a southern foreslope as well as a platform margin in a continuous oblique section. So you have all of this exposure of a snowball earth, and as I said earlier, it's rare to even get such exposures of snowball earth because you have only 1.5% representation, and on top of that, they are located in the foreslope area and not on platforms. So this here is a restoration of the platform as well as its continuous foreslope with carbonate strata colored blue. So here, carbonate strata colored blue. And the presence of thick non-skeletal carbonate indicates the deposition in a warmer part of the Neoproterozoic ocean. The older Cryogenian glacial sequence is colored purple and was thin rift in age. This is the one that we name in Namibia the Chuos Formation. And the younger glacial sequence is colored red and was post-rift in age. The younger Marinoan sequence is best developed in the foreslope zone of Fransfontein Ridge. And this is where you have your Gaup formation. This is the red portion there. So during this younger Marinoan Gaup glaciation, the ice sheet over the platform was contiguous with a thick floating ice shelf or sea glacier of global extent. Erosion and transport by the ice sheet resulted in the construction of a submarine moraine near the grounding line, where overflowing ice began to float. A kilometer thick ice shelf combined with a kilometer scale drop in sea level due to ice sheet buildup caused the grounding line moraine to form on the foreslope. Therefore, you have this situation. So we are looking now at the different stages. So as I said earlier, the grounding line moraine was developed on the foreslope and not the platform. Growth of the ice sheets was sourced by sublimation of the equatorial sea glacier. Successive Marinoan stages show ice shelf thinning with carbon dioxide-induced warming. Surface air and brine temperatures in each of the stages are indicated. So you see a pre-Marinoan situation with the sea touching the platform, and then with the development of thick ice sheets, you have different temperatures. So you have a fairly low temperature of the brine, but eventually your temperatures start increasing as we go on in time. So what happens here is also very interesting. You see this sort of little area, indented area. So surface air and brine temperatures are indicated. Isostatic compensation is shown, and tectonic subsidence, this is what I was showing here, is indicated by higher sea level after meltdown. So once these ice caps started melting down with the increase of carbon dioxide, you have this thick grounding zone moraine wedge developing here and the subsidence of part of the outer platform. So here is the first of 4 slides illustrating how the glacial record is expressed on the foreslope of Fransfontein Ridge. The base of the glacial sequence is an erosion surface representing the early ice maximum when the ice shelf was thickest and the grounding line deepest in response to low carbon dioxide and high planetary albedo. So this is in this portion of the section. Planetary albedo, I don't know if you guys are familiar with this term, is the fraction of the incoming solar energy scattered back to space by Earth. So if we talk about a high planetary albedo, we are talking about lots of sun energy being scattered back into space. So below the erosion surface is a falling stand fan. So this is this whole portion here. And it is composed of oolite-classed debride formed in response to falling sea level due to pre-snowball ice sheet growth at the higher latitudes. So this is what you are seeing here, oolite debris in the deposits. So we are looking now at the next portion, which is the stratified diamictites. And the moraine itself is composed of two intertongued types of carbonate diamictites, stratified and massive. So the stratified one is in the purple, and then the massive one is in the magenta color. So this is what stratified diamictites look like. So that's in your pro-glacial. They were deposited seaward of the grounding line. So you have this, so it starts in the early Marinoan and then proceeds into the mid-Marinoan, and you have this deposition of these sequences. Then we've got the massive non-stratified diamictites, and they were mainly deposited beneath the grounded ice as melt-out tills, and some, however, formed as rain-out tills at the grounding line where ice touches the seawater brine. So once again, you can see how from the mid-Marinoan to the late Marinoan, you have this grounding zone moraine wedge increasing in thickness. So massive diamictites on Fransfontein Ridge contain countless lenses and channels of size-sorted and current stratified deposits, indicating the production of subglacial meltwater. Warm basal ice is predicted from geothermal warming of snowball ice sheets due to their slow accumulation in the cold, dry snowball atmosphere. And this is the fourth slide showing the sections. So when the ice shelf finally collapsed and the ice sheets melted down, the foreslope was draped by chocolate brown, iron-rich stratified diamictite. So this is what you are seeing here, and you can see all this nice dark brown color showing us iron-rich deposits. And these were choked by ice-rafted debris of all sizes. Abrupt cessation of ice-rafted debris was followed without a break in sedimentation by a regionally continuous cap dolomite. And this is what you are seeing at this top here. And this is diachronously draped over the whole foreslope and the platform as well. So this is, as I showed you earlier, this is what you are seeing here. And of course, during the early Ediacaran, a rise in sea level, no ice. All right. So what is the scientific tradition of this place and of snowball Earth in general? You will be surprised that during the 70s, 60s, 70s, and 80s, A lot of PhD works, postdoc projects, were done in this area, and they still remain one of the baseline information for snowball Earth. So you can see some people like from Brazil and so on. And then just here again showing the closely spaced section, logging and stratigraphic reconstruction that had been done over the years, showing your cap carbonate on top here, and then, of course, your glacial deposits here. So the polar glacial sedimentologist Eugene Domack and students documented the grounding line lithofacies and used carbon isotopic compositions of glacial debris to fingerprint depths of glacial erosion, given isotopic profiles of the platform and of the pre-glacial succession. Two sources were evident: shallow erosion on the platform and a deeper notch or bench on the upper foreslope. So this is what I was also showing you, the notch, possibly marking the equilibrium line of the ice sheet during the later Marinoan when the ice flux was highest. So obviously with the weight of the ice, it was pressing down and formed this little bench. Detailed lithofacies mapping is still being done, but now using a drone. So if you cannot be a bird, use a drone or be a drone, then you can do mapping in very high places. So yeah, this is just almost like a little joke. And then in some of these areas where very few people stay, the children are always interested when scientists come along, and they participate in collection of samples, in this case here, volcanic tuff, bentonite samples used for zircon, uranium, lead dating. And this is the author of this site is Paul Hoffman here. And so what are the main arguments for a geological heritage status? Number one, we have the critical support for the snowball Earth hypothesis from great sea level changes and massive carbon cycle perturbations that first came from the Otavi group in Namibia, from especially this Fransfontein Ridge. Then we also have the Fransfontein Ridge, which is best known as an example of snowball erosion and sedimentation across the foreslope of an ambient warm water carbonate margin. And then thirdly, the cryogenian snowballs involved the most extreme sustained cold and warm climates in the geologic record, pre-existing alpine and polar ecosystems that managed to move to the equator and survived the cryogenian glaciations, gave rise to the surface biosphere that we know today. Thank you very much for your attention.